Good morning, everyone. Really glad to see you here. So this is the parallel data analysis tutorial. So I'm Matthew Rocklin. This is Aron Ahmadia. This is Ben Zaitlen. We'll be helping you guys today. Today's tutorial is not about any particular tool. It's about generally parallel programming in Python. I have a few different programming paradigms, and we'll try to help you figure out which sort of paradigm tools to use at which situations. So again, we're not talking about any particular framework, any particular tool, it's sort of generally about parallel programming. If you were in this session last year, it's going to be more or less exactly the same. There's a parallel programming tutorial happening right now in room 105 about Dask, if you want to go to that. So if you're in that situation. Okay, while I'm talking, a much better thing to do than listening to me speak is to go to this page, github.com/pydata/parallel tutorial. That has instructions on how to start. How we're going to break this up? So the first half of the class will be mostly on your laptops. And then for the second half of the class, we're going to run a cluster. So Google has been generous enough to donate some credits to us. So we'll be working on clusters on Google Cloud. I'm going to talk for the first few sections, then Aron will take over, then Ben will take over. While you can ask for help. So we should all practice waving for help wildly if we have questions, and someone will come by, or most of us are pretty friendly. So please ask for help. So while I'm doing this, you guys should be up here downloading this repository. This will download a bunch of notebooks onto your machine, and we will use the Jupyter Notebook server to go through some exercises. Later on in the course, it has been mildly changed since like 7, 8 p.m. or something. So in the first part of the course, we're going to use your local machine, if convenient. If that doesn't work, you'll switch to the cluster immediately. That's fine. For the second part of the course, we're going to be using a cluster, which will be this link. When you go to that link, eventually, there'll be a big blue button you should press, hopefully just once. So we want to make people sort of aware this is a very satisfying button to push, but please everyone push it, one time, and maybe not yet, maybe later on today. So resist the urge.
All right. We would all like you to push the button.
No.
Don't push it.
Yeah.
Oh no, just me.
Yeah.
All right, don't push the button.
So due to a scheduling snafu, we're using the same cluster for 2 tutorials at the same time. And so Ben, who's in charge of the tutorial, has been sort of sweating pretty constantly for the last 24 hours or so. So we're not going to press the button yet. But when you press it, if it takes a while, don't press it again. Just wait. Okay. But for now, single machine. So, any other introductory material we should talk about?
We're using the Slack room. I'll try to keep an eye on it. Yeah. So we're going to be using the Slack room. I'll keep an eye on it when Matt's talking. Matt's going to keep an eye on it when I'm talking. And that's the only thing I wanted to say.
Okay, so again, if you're having trouble setting things up, you should not be at all ashamed of that. 50% of the class will have problems starting things up. You should now start waving your hands wildly, and someone like Ben or Aron will swing by and help you out. You can have one person who's having trouble swing their hands wildly. This is going to be really awkward until someone does it.
This is for pretend.
Yeah. Yes!
There we go.
Great. And so someone can go and help. Okay. So I've downloaded this repository, and I'm going to follow these instructions to create my conda environment, which I've already done. And I'm going to enter this conda environment, and then from there, I'm going to start up a Jupyter Notebook server. And then in the notebooks directory, there's a set of notebooks. We'll be running through these throughout the course. We're going to start with this first one, map. Okay. So before that happens, a little bit just fundamental material. So we also made these tutorials with Min, who couldn't be here today, but he works on Jupyter and at Simula. So, okay. So the first part of the course, we're talking about 3 sort of ways to think about parallel programming. We're talking about embarrassingly a parallel map, which is a very common case. about more flexible task scheduling with submit, which is maybe a bit more flexible. And then we're talking about collections, big data collections like Spark or data frames, that sort of thing. So with the simplest case, map. So you have a function and you have a bunch of data. You want to call that function on many pieces of that data. This might be parsing many files, or it might be running some computation across many inputs coming at you. Typically in Python, we might write this as a for loop, or with list comprehension, or with this map function. So map, we give it a function and we give it a list of data, and it produces for us a list of outputs. The nice thing about this last option is that we can rewrite map to run in parallel, and many programming frameworks have rewritten map to run in parallel. So, for example, there's the concurrent futures thread pool executor or process pool executor. And here we make an executor, we give it our function and our list of inputs, and it gives us a list of outputs executed in parallel. This is a very common theme. So many libraries follow this exact same system. Right? You import some object from some library. It could be IPython parallel, it could be joblib, it could be Spark, it could be Dask, it could be something else. You call map, and you get a list of outputs. So let's walk through this first notebook. Okay, so
does everybody have the notebook open? Anybody, if you don't have the notebook open right now, raise your hand.
So as part of setting up, you were asked to run a Python prep.py script, which creates a lot of fake data inside of your repository. This is daily stock data that we've interpolated to be like about 1 gigabyte in size. So it's easy to download, but it takes a little bit of time. I forgot to run it, so I'm going to sit here for a minute or so while it creates all this data, writes it down as CSV, and then as JSON. Yeah, so it may be less than 1 gig, but somewhere around that size. If you run into problems, you should wave your hands wildly. Yeah. Okay. This is actually somewhat awkward because I should have run this beforehand. Any questions so far? Okay. So let's take a look at the data that we are generating. So inside of this directory, it's generating data for us. And if we go to, say, the IBM directory here, we'll find many CSV files. Each of those CSV files is a time series of data with closing prices. These closing prices are representative of the kind of things you'd see in a stock, but they are not actually actual values. You should not trade the stock market on this data. But we have many of those files. This is sort of a common case. Here we're looking at financial time series, but you can imagine these coming from a detector. You can imagine these coming from a simulation that's running. You have many files, and you want to do sort of similar operations on all of those files. So what we're going to do with that data is we are going to also generate some JSON data. And then for each file name, we're going to load in that data as JSON, which can be somewhat expensive. We're going to write it out as a better format, as an HDF5 format. So if you were at tutorials yesterday, you might have seen the HDF5 tutorial, which is a much more efficient format. So this is something we want to do. We just want to load in data, which is expensive, and then write it out as a more efficient format. This we can do on every file name independently. So we don't need to do any sort of coordination between these files. So it's a very good opportunity to use map, which again is this case where you want to do the same function many times in parallel without any coordination between the two. Great. So I've run my prep script. I'm just going to run through this code. And this is sequential code. Right. This is code that we've done on our own time, using Python. Now we're going to try to parallelize this code to make it run faster in the future. So a lot of these notebooks will have examples that are sequential code, and it'll be your job to parallelize that code with some of the techniques we're going to play with. Okay, so that used a library. So we ran this code, and it ran, and we can see it running through all of those JSON files. And we're using this SnakeViz magic, and SnakeViz is a profiling tool. This helps us understand the kinds of costs that we experienced in running this code sequentially. So before we parallelize anything, it's very, very nice to understand what is taking time. And we'll see more examples of why that's important in the future. So have people used SnakeViz in the past? Raise your hand if you have used SnakeViz. I've seen like 3 hands. So this is my computation. This is a visualization of my computation. This is the more sort of standard output you'd see from, say, the Python cProfile module. We're going to visualize that here. So the inner circle is my entire computation, and that was a function here. It's exec. You can see in this area over here. And that called a function in my module, which then called a function. It was a list comprehension, which is then called JSON loads. So here we're seeing that the JSON loads is around 60 to 70% of the total runtime of this computation. So as we go out further and further in different circles, we're seeing the fraction of time that our computation is spending in that circle. JSON loads called some string decoding functions and some regex functions, and you can see the breakdown of the costs here. And understanding this breakdown will help you make a lot of decisions about how and which tools to use when parallelizing. The other section over here is doing a lot of pandas things. So this is converting all of our lists of Python objects into NumPy arrays or pandas data frames. But the final number is that it took my computer about 13.6 seconds to run through this computation serially. And so our objective for this notebook is to run through this computation in parallel to accelerate, to reduce that total runtime from 13 seconds to something lower. Yeah, so SnakeViz should open up automatically for you if you have SnakeViz installed, which you should if you are running the content environment. And if you're using this % SnakeViz magic. Are other people seeing this tab or not seeing this tab? Who's seeing the tab? Who's not seeing the tab? Okay. Okay, yeah. It doesn't actually matter. You'll be totally fine. If you want to avoid SnakeViz, you can use the time and magic, and that'll be less informative, but still pretty useful. I'm using Chrome, but it shouldn't matter. So we ran that again and took around 10 seconds. So there's some variability there. Okay, so we have a problem that we've been asked to parallelize, this just very simple parsing of JSON data. And we're going to parallelize it using a library called concurrent futures, which is built into the standard library and has this map function. But again, map is common in many, many systems. So if we have code that looks like a for loop, oops. If we have code that looks like a for loop, we can rewrite it as list comprehension or using map. And then if we have code that looks like map, it's very, very easy to replace map with executor.map. And this allows us to parallelize code in a simple way. So we have code that looks like a for loop. So now our goal is to rewrite this code to use something like map and then switch in executor.map. So as an example, here's a much, much simpler example, not our full computation. We're going to sleep for a second and then add 10 numbers, add 1 to 10 numbers. And this takes 8 seconds, 8 numbers, sorry. So to parallelize that, we can import process pool executor. We now need to break open all the things that we did in our for loop and make a small function out of them. So here we're making a function slow increment, which sleeps for a bit of time, again, to simulate work, and then returns x plus 1. And then we use executor.map, calling that function on this list of data. And this now runs not in 8 seconds, but in 4 seconds. So it has moved our function to four different processes, because my computer has four cores. Called the function in each process, and has brought them back together again. So this is sort of the simplest possible thing you can do with parallel programming. Yeah? Yeah, so you may notice that there's this recommendation that if you're on Windows or even sometimes on Linux and Mac, you may prefer this other library, Loki. That's because sometimes with using processes, it's hard to work with functions that are made dynamically, just based on how Python serializes functions. Windows users, you don't have fork as an operating system level, which makes it hard to send these things around. But Loki is a great library. It's a drop-in replacement for concurrent futures, and it handles all these problems for you. So you just use Loki all the time, you'll probably be pretty happy. Yeah, so if you're on Windows, you might want to pip install Loki. I already have it installed. And then you would, instead of importing this from concurrent futures, import it from Loki library. And that would do just the exact same thing. Okay. So now here's an exercise. So again, this will be a combination of sort of me talking at you and then you guys doing exercises. So we have the sequential code from before. Now your objective is to rewrite the sequential code and parallelize it using this process pool executor map. So it should be very similar to the example above, but now with this more concrete example. So let's come back at 8:30, so 10 minutes from now. And in the meantime, we'll work on that exercise. If you have questions, please wave your hands wildly.
Exercise and is ready to move on. Who would like some more time?
Okay, it seems like most people are pretty much ready. If you're not ready, so people have different skill levels, come here with different experiences, they do different things. If at any point you want to just see a solution, the solutions are here available for you in these cells that start with load. So this is how we solve the problem. We took the, so to make the solution appear, you run the cell that starts with %load. And that will load up a file that's in your directory that has all the solutions for you. So I'm going to press Shift-Enter, or if I'm using the notebook buttons, I can press sort of run cell button. That will replace that cell with the contents of that file, which have a solution for us. So we've taken the body of our for loop and converted it into a function, which takes in a file name. So this looks very much like what was here. This body of this for loop. Oops. We created a function. We created a process pool executor. And now we call executor.map, giving it that function, and then the list of file names to run that function on. And then we can time this, and we can see if we get any speed up. And we do. We get it runs around 4.7 seconds, about twice as fast as what we saw before. So we used 4 cores and got a 2x speed up. So it's not perfect parallelism, but we did get some benefit, which is nice to see. So this is a very, very common situation. A bunch of files, you want to parse them, want to do some arbitrary small computation on them. We just call executor.map on given that function. The hard part here tends to be taking our for loop and the body of that for loop and constructing the right function out of that body. However, as an example here, parallelism is often a way to accelerate things, but often not the best. So we noticed when we were looking at our profile that about 70 to 80% of the time was spent in this JSON.loads function. Now, if we Google around for fast JSON in Python, we'll encounter this library UJSON for ultra JSON. And so we can run the exact same computations sequentially using this UJSON library instead of JSON, and it runs again in around 5 seconds. We still get about a 2x speed up just by switching to a faster library. So while parallelism is often a good solution, it is sometimes not the best. There's sometimes even simpler solutions that are out there. Or we can use both. Right? So import UJSON as JSON. We can run our parallel programming solution again. And we run in 2.5 seconds. So people often reach for parallelism because it's sort of an attractive tool these days, but there are many other things you should also look at. So we're going to move on. So map is often very good when you have, again, one function applied to a list of inputs. Sometimes you're faced with a situation that is more complex. So on sort of the other extreme side of that spectrum of ease, there's cases where you have code that is obviously parallelizable. So here we're calling these functions f and g, and they can happen in parallel. They don't depend on each other. But it's not clear how to turn this into a map situation. So I've got these two nested for loops. I'm iterating over two collections based on some predicate on those values, and then calling either function f or function g on those inputs. Again, this is parallelizable, but it's not map. It's something else. And so the question arises, how do you handle these sort of situations? So we're going to talk about submit, which is sort of a counterpart to map. And many frameworks implement both map and submit. Here we're going to use concurrent features again, although the API will be implemented in many places. And here what we're going to do is we're going to, instead of calling a function, f, on some inputs, we're going to submit that function and those arguments to our executor. So previously, we called f by saying f parenthesis inputs, and now we are instead submitting f to run somewhere else. In this case, it's going to run on a separate thread, but also run a separate process or on a separate machine with different executors. So this allows us a lot more freedom when our situation is a bit more complex than just a simple map situation. After we've submitted all of those tasks to run, eventually we want to wait until they've finished. And so for that, we use the result method. So submit gives us back a future object, sort of a pointer to work that will eventually be finished. And if we want the result, we can call the result method on that future. So here's another sort of situation. So you're going to call submit. That's going to immediately submit some task to run on some other parallel resource, like a thread or a process. It immediately gives us back a future. We can do other things while we let that thing run in the background. And then later on, we call result to get the finished result. Those other things we're doing could be submitting more futures. This allows us to be parallel. So we can, in fact, implement map by just calling submit many times, creating a list of futures, and then waiting all those futures to return. The nice thing about this is that it allows us to mimic our sequential code relatively closely, even if that sequential code is somewhat complex. Okay. So we're going to start with the HDF5 files that we created in the last section. So here I'm on notebook 2.
Just going to pause you.
Yeah.
If this list here is empty, then you need to go.
This list here is empty. You need to go back and run notebook 1. This is going to be empty by default unless you've successfully completed the first notebook.
Yeah, so as part of the first notebook, we ran the sequential computation, which created all these HDF5 files. You don't need to complete the first notebook, you just need to run the first few cells. You will then have a bunch of HDF5 files. If you don't have those files, you should wave your hands wildly. We're going to, so we're now going to do our sequential computation, and we're going to parallelize it in a moment. So we're going to load a time series from each of those files and store it in this dictionary series. So series has values that are keyed by file name, like data, JSON, AT.h5. And those are pandas series. And we can plot those. These are time series for one particular day of data. And there are a variety of series in here that all have different reactions to the market over time. And our scientific objective here is that we want to find series that correlate well with each other. Particularly, we want to find the two stocks that trended together the best. So there's a method core for correlation. Let's do this. So we're going to iterate over each of our file names, pull out our series, then call the correlation method. And this will find us that there are two series, there are two stocks, AET and LUV that correlate well together with a correlation of 95%. So let's look at those briefly. So that indeed those two stocks do seem to sort of trend similarly. So this is useful if you're playing the stock market, you want to understand how different sectors of the market move together. So let's look at that computation for a moment. We did an embarrassingly parallel thing. We could solve this with map if we wanted to. We're actually not going to parallelize this. We're just going to leave it as is. Then we followed with a doubly nested for loop with an if statement in the middle. So this is a little bit more complex than a map. And then finally, we did a reduction. We took all of our results and found sort of the single best one. That's sort of fast enough. We're not going to worry about parallelizing it. We're just going to focus on this middle section here with these two for loops. That's what we're going to try to parallelize. First, we'll look at an example. So just like our previous example with adding numbers slowly, we're going to look at adding two numbers in a future on some separate thread. So here I've constructed a thread pool executor. I've constructed a function that adds two numbers but sleeps a little bit of time to sort of simulate actual work. And submit, you may notice, returned instantly. So if we run that in a separate cell, we see that it ran in less than a millisecond, even though the function is going to take a second or more. But that future, in the meantime, has finished. So we can now get the result. So concurrent futures allows us to submit tasks and then wait for them to finish when they're done. So we have sort of sequential code here, like this for loop. We're going to call this slow add function 10 times, and it's going to take around 10 seconds. Or we can submit 10 times. That'll create 10 futures. And then we're going to wait for all of those futures to finish in this following line. And because I have around 4 cores, I have 4 threads, but I have 10 elements, it's going to run in 3 seconds. So it does 4, does the next 4, and then it does the following 2 at the end. Yeah, so the question is, hey, in our example up here at the top, oops, here we go. Yeah, example up here at the top, you're computing the correlation of series A versus series B, and later on you're computing the correlation of series B with series A. And that seems like redundancy, because we know that correlation is symmetric in that way. And so we could be much smarter. We could, again, eschew parallelism entirely and get a 2x speed up by doing that. So it's a very good point. We can often be smarter and reduce our compute time, not by parallelism, but by choosing better algorithms or being more intelligent about our situation. So that's an excellent point. Thank you. Yeah.
Hey, folks, who is having an issue where they're getting the key error? Okay, great. I have a fix for you. So for some reason, this first file, aet.h5, for a bunch of you is corrupted. So what we're going to do is all the way up here on the top, where you say file names equals sorted on this glob, we're going to try and do a live fix. And what I'm going to do is I'm just going to grab everything except that first one. Okay, and then try and execute this next one. And if you still get that error, raise your hand. If it's gone away, raise your hand and give me like applause, because that was actually live coding. That hasn't fixed it for you? Okay, fixed it for everybody else? Perfect. Okay, so just grab that first file and chuck it off. I don't know what's going on there, but we're moving on.
Thank you, Aaron. Okay, so here's a simple case in which we've sort of re-implemented map using using futures and submit. So in our exercise, so we're going to do 2 exercises. One is, yeah, question mark? Yes, question is, does the work happen when you call submit or when you result? When you call submit, you're putting that work into a queue, and there's a group of threads that are all watching that queue, and are going to pick off work whenever they can. Result is going to block until that task has finished. So the work happens as soon as is possible, but not immediately, because you might submit more work than you have threads. That being said, There are many implementations of concurrent futures. So this is an API that's in Python. It's implemented in the standard library. It's implemented in IPython Parallel. Dask implements it. A project called Scoop implements it. And they may all choose different policies depending on maybe they want to run something on a certain machine because it has a GPU. They might make different decisions. So you're giving control up to some other system to make those decisions for you. But generally, they'll run as soon as possible. That's a great question. Thank you. Okay, so we're going to do 2 exercises. One is going to be very abstract, using just sort of these slow functions. And then one, after that, we're going to run on our full computation. Let's do this simple one for the next about 3 or 4 minutes. I'll come back, give a solution. If you sort of finish in time, move on to the next one. So, you got a question over here. Yes, the question is, can I pass any object into submit and get any object back? In the case of the thread pool executor, yes. You're just calling Python things. If you're using something like processes, that function or those objects would need to be serializable because you're moving them to a different Python process. Got to be turned into bytes, shipped over a wire, reconstituted into an object. This usually also works, but it's sometimes more complex. But in our case, absolutely any Python thing. You can make your own classes, you can make your own functions, it's not going to matter. But this is also going to depend on the implementation of concurrent features that you're using. So it's a great question. Thank you. Okay, so I'm going to briefly give the solution to the first sort of abstract problem. If you've already moved past this, feel free to ignore me. So again, here's a sequential version. It's going to walk through the lists 1 to 5 twice in a nested for loop. And if I is less than j, it'll call one function. If j is less than I, it'll call another function. It'll take around 20 seconds because we're calling these things about 5 times 4 times. And so what I'm going to do is I'm going to take this code, and instead of calling the function immediately, I'm going to submit that function to run on the thread pool. So I can't use the parentheses anymore. If I use the parentheses, I'm going to call that function right now in my Python process. I don't want to do that. I want to delay that function to happen later. So I'm going to give the function as an argument to the executor. Do it also down here. I'm no longer getting results. I'm not getting these futures. I'm going to change the name of my variable to futures. And that gives me now not my concrete answers, but these sort of pointers to remote results that are going to be happening eventually. So I'm going to now wait till all of those finish. Let's run that. I have, again, 4 threads or 4 cores running, so this runs at around 4x speed up. And again, the advantage here is that we had code that was not entirely clear how to parallelize it with map, but we were still able to get a nice parallel solution just by mostly copying and pasting the code and making a few small adjustments. So submit is very flexible in that way, which is pleasant. And again, if you want to, you can always look at solutions, and they'll always be there for you. Okay. How many people, just show of hands, how many people are already done with the actual exercise for the notebook? Okay, great. Let's take a few more minutes.
So this is an additional challenge for the 12 gazelles that are ahead of the rest of the class. Try and batch this so that you only submit 10 jobs at a time, but then you take all of the results together at the end.
While people are finishing up, if you've already finished, something you might want to try is swapping out your thread pool executor with a process pool executor. We'll talk about this a little bit more, but it's the same API. You have your choice between using many threads in your same process, or using many different processes. And if you use a process pool executor in this problem, you'll find maybe your solution breaks, maybe it doesn't, and maybe you get different performance, maybe you won't. So it's interesting to try those two. In the last notebook, we use a process pool executor. In the notebook, we use a thread pool executor. And is there anything about why we made those choices? We'll get to that later on, but if you're done right now, that's something you might want to try out, just to sort of experiment a little bit. Sure, yeah. So the question is, what happens when an exception happens? So let's just try that out. So let's make a function, div, which takes 2 elements, x and y, and returns x divided by y. Make a future. We'll submit the div function on maybe 1 and 0. So this is like 1 divided by 0. So nothing's happened so far as I can tell. Let's look at that future. So the future looks like it's finished, it knows, and it says, hey, I raised a 0 division error. So now when I try to get that result of that future, then I actually get my result raised locally. So the exception happened on the other thread, and we didn't get that locally because like there's no way to sort of block your Python process and say, hey, like an exception happened a long time ago. When you try to do something with that future, it then alerts you, hey, you actually can't do this anymore. This future caused a bad result. So if you're in your sort of normal working of your program, you'll run into the futures eventually, run into the errors eventually, once you depend on the result of the future. What's nice actually in this case is that you can actually see the traceback. Everything sort of looks pleasant. Actually, I'm sort of curious to see if IPython, if Jupyter Notebook, let me go in and inspect. Yeah, so you can even inspect the state of these things, which is nice. Debugging in parallel programming is often hard. The nice thing about the thread pool executor is happening in the same process as your local system. And so you get to share all of the state. You have to move data around and be very efficient. Has anyone tried using the process pool executor on your problem? So what happened? It's like 5 times slower. Is it slower or faster than your sequential version? Okay. It's slower than your sequential version. Okay. Yeah, so in that case, we're actually moving data between different processes, and that can be really expensive.
I think you just handed half the students a sharp knife. Once you start debug, how do you get out of it?
Yeah, so if you're in this state, if you have to like try to do something else, like it's just going to block because Jupyter is waiting for this debug thing to finish. So if you press Q and then press Enter, you get out of that debug section. Thank you, Aaron. Yeah. If that doesn't work, just restart your notebook and you'll be fine. Okay, so let's look at solutions. So we pulled out. So I saw many people doing series a.core, and that's totally fine to use methods. I personally just created a separate function. Thought that was a little bit simpler. And then instead of creating a dictionary of results, we create a dictionary of futures. And instead of calling our function, we submit that function to happen remotely. When we're done, we find all of our futures, which are now in a dictionary rather than a list, and we call result on them, returning back a dictionary that looks exactly the same, here with the dictionary comprehension. Let's time this. So how long did our sequential version take? Sequential version took 500 to 600 milliseconds. Parallel version took around 400 milliseconds. Not a huge speed up in this case. And you can ask questions about why that might be. In this case, we actually weren't very computationally bound. We're sort of maybe relying on more memory bandwidth rather than CPU bandwidth. So we're not getting a whole lot of speed up. Okay. So again, in the last exercise, we used process pool executor. This exercise, we used thread pool executor. From our programming experience, they're the same. They look the same. They have the same API. We operate on them the same way. They have very different performance characteristics. With threads, they're happening in your local process. So your IPython program that's running has all of the computations happening in the same program. So they can share data very easily between each other. They can all access the same arrays, the same series. It's all very convenient, the same methods. Process pool executor, using many different processes. And there, you have to move the data from your process over to another process, run the function, and then move the data back. That can be slow, but also be very good if you need to run different processes. For example, if you want to avoid running into the GIL, which is a problem that sometimes plagues pure Python code. A general word of, and if that doesn't make sense, that's fine. Generally, when you're using NumPy or Pandas or scikit-learn, you should use threads. If you're using pure Python things, dictionaries and lists and JSON parsing and text, you probably want to use processes. That's sort of a general rule of thumb, and it's more complex than that. Those are some thoughts. Someone also asked, if I'm using threads, can I just append to a list in my function? And the concern there is that list, if you have many threads operating something, you might be unsafe. So sometimes there are some concerns. For example, if we call the read HDF function from pandas, that function is actually not thread safe. The HDF5 library is not thread safe. So if we use many threads here, actually it was going to work. In most versions of HDF5, that would fail. But I guess HDF5 maybe more fixed now. Okay, so HDF, what was the version number? Okay, so a recent version of HDF5, or H5Py or HDF5? Okay, so HDF5 is now thread safe. So last time we gave this tutorial, this exercise broke. And it broke in a terrible way that caused the entire Python session to just tear itself down. There was not an exception, it was just like a seg fault. That's okay. If we were to downgrade HDF5, but apparently HDF5 has now been fixed and is now thread safe, which is great to hear. So I now need to make a better example. But threads are sometimes dangerous. Okay, so we're going to move on. So we've seen map and we've seen submit. Map is a very common case, but very simple. Submit is sort of a very flexible tool and handle any situation. A nice middle ground is these big data collections. So sometimes you're given a restricted API. So this might be like with Spark, you get map and filter and group by and join, or it might be like an array programming system that's parallelized. You have matrix operations like matrix multiply and LU solve and Cholesky factorization. Or you might have something like data frames or something like the SQL language. And so in these situations, as long as you are able to constrain your programming to these APIs, you are now able to, they will handle all the parallelism for you. So this is very, very good if your problem fits one of these cases, because it'll be more automatic. So sort of map is sort of one extreme, the very simple case. There's collections where your computation is more complex than map, but still fits into a regular structure, and there's things like submit for very sort of arbitrary computations. So we're going to look at sort of the classic sort of Spark RDD kind of API, which has functions like map and filter and group by and join. And these operations can be parallelized, something like Spark or Dask or whatever will handle them. And you can chain them together. You can use many of them together to create more complex operations. So in this notebook, there are two versions of this. You can use this with Spark or with Dask Bag, which is sort of a project that looks like Spark. Dask does many things, but it also does this thing. I'm going to use Spark. I work on Dask. I feel a bit bad representing it, so I'm going to use Spark here. But you can use either one. The notebooks will be more or less identical. Okay. And if you need to install PySpark separately in order to use this. If you didn't, that's fine. Use the Dask Bag thing. The lessons is exactly the same. Okay, so we have our code from before. Right, this is the exact same application we did in the last exercise. We're loading a lot of series from HDF5 files. We are then computing correlations between all of these different series. And then we're finding the maximum element, the best pair. And we're going to do that using operations like map and Cartesian or product and filter and max. So it'll help us build out this computation, but breaking it down into map steps and product steps and other map steps. So when I'm making something, I'm going to use Spark here. So when I start up Spark, I need to create an object. This is like a thread pool executor or like a process pool executor, but has different methods on it now. I can take a list or a Python iterable and create from that Spark RDD or Spark collection. And this is now handled somewhere. These are actually living in different processes, maybe on my computer, maybe they're living on a cluster, I'm not quite sure. If I want to, I can bring those results back. Okay. So I went from Python list out to Spark thing, back down to Python list. Now, in the meantime, I can do some computations. So I can do things like map, and I can give it some function which will square every element. And it gives me back another RDD. And so now I could do that again. I could do map and then dot map again. I can call many different functions in a chain. Or when I'm done with the computation, I can bring that result back. So I might map something. Here we're seeing filter, but I might decide to map and then filter. So I'm squaring all the elements, and I'm bringing back only the even ones. And the more operations we chain, the more Spark knows about how to push those together and operate on them, on different machines at the same time before bringing them back. We avoid a lot of communication by having lots of operations to chain together. Another operation that'll be, I think, particularly useful for this exercise later is Cartesian. So we have 2 collections. So this is list 1 to 5, this is list 1 to 5, and we're going to find the Cartesian product. So every element of the first pair with every element of the second pair. This is kind of like a nested for loop. You can imagine maybe having a nested for loop and printing every element. So again, we can sort of combine these operations together. We're going to map all the elements. We're going to Cartesian product it with the original, and then filter out where all of the first elements are even. So this is how things like Spark or DASBag look. You are given a fixed set of operations, again, like map, filter, group by, join, Cartesian, and you combine them together to perform your computation. As long as you stay within this world of operations, these projects will parallelize for you. In this case, we're using just my local laptop, but it can scale out to a cluster, which is nice. Okay, so the exercise for this section is to do the same computation we did previously. Here's our sequential code. But now we want to do that same computation using Spark RDDs. So we're going to have an RDD, which is all these file names. And we want to walk through this code and identify, this part looks like a map. I can map a function across all those file names. This part's a little more complex. How do I translate this into a bunch of Spark operations? So let's do that for a while. Aron has kindly set up a checkbox on the Slack channel. When you finish an exercise, if you wouldn't mind checking that box, it would help us understand sort of how people are doing. Okay, so let's come back to this in a bit.
If you're trying to run Spark locally, make sure that you have Java installed locally. Oftentimes OS X machines come with Java, but there's a few instances that we've seen where it's not installed.
Someone asked in the Slack channel, is Spark doing all of these group at a time, or is it compiling them and doing them all sort of sequentially? So is the same process running through the map and then the filter and the Cartesian, et cetera, all at once? And Spark is being clever here. It's for any given group of data and group of file names, it's mapping the read HDF function on them. Then it's filtering, then it's Cartesianing, then it's filtering, then it's going down. So it's being smart. And generally speaking, these big collections are good because they can be a bit more smart. Something like concurrent futures with submit, it's so flexible that it's very hard for concurrent futures to be intelligent about scheduling your tasks and being very clever about them. Something like Spark, because it's restricting itself to a smaller API, or SQL, for example, it's restricting itself to a smaller API that it can reason about, it can be very clever about where to send computations, reordering computations in some cases. Let's look briefly at the solution. So we ran our code, it ran in about 1.7 seconds sequentially. We've parallelized this with Spark or DASBag. The exercise will be the exact same, except for this term. So we have our file names, and we parallelize them out to an RDD. So now all of our 20 file names are living on different processes in Spark-controlled Python processes. We're then going to ask all the processes to turn those file names into series. We're going to Cartesian product those series with each other. So now we have pairs of series. We have every possible pair. And we're going to filter out all of the pairs that are the exact same. So we're going to remove those elements where we're sort of comparing IBM with IBM. Then we map this correlation function, and we find the maximum. So 2 questions that come up. 1, why is this slower than running sequentially? And then 2, this is sort of complex. We got all these sort of dots, all these sort of method chaining. And this is a stylistic question. You could also have written this as many different individual lines. Maybe just series equals this. Series equals series So we can also put this on many different lines, and that's fine. This is just a stylistic choice. Some people prefer to chain. Some people prefer to have them all in one operation. So that's just a Python question. Okay, so that ran. I should have called time on that. This is going to take a fair bit longer, and that's because. Or does anyone have thoughts on why that might be? Even though we've parallelized this, why is it slower? It took 8 seconds. You already know. Yeah, want someone else to answer. So sequentially, this ran at about 1.5 seconds, and in parallel, it took 8 seconds. Why did my code slow down when I ran it in parallel? Yeah. Is there a lot of setup, right? So we're starting all these processes. We're then we're calling some sort of Spark setup code over there. Did that take a long time? That does often take a few seconds. In that case, that's not the only thing that's going on. There's someone else up there who has a thought. Yeah, so the answer is what has to move data between workers, right? So think about our computation. We have all these file names. Those are very cheap to move around to all different processes. We convert all those file names into pandas series. That doesn't require any communication. All of those processes now just have series. But in that Cartesian product step, we have to move every series to every other series. That causes a lot of communication. And communication can sometimes be costly. So moving data between these different processes. So Spark is really good in that it can scale out to a cluster. It's used to running in a distributed environment where it's always got to move data between different computers. But that movement of data can be expensive. And our local laptops, that actually ends up hurting us a little bit. And we spend much more time moving data around than we spend in these very small correlation functions. So sometimes parallelism can slow us down because there's extra costs, there's setup costs, there's communication costs, etc. From the Dask notebook, you can do the same computation with Dask, and you can switch out to using threads or single thread, and you'll find a speed up.
Similar to how we use Snake before, is there other tools to help see data movement was expensive?
Yes, question is, are there just like how SnakeViz helps us understand the performance in our local Python process, are there other diagnostic tools, maybe visual diagnostic tools that help us understand performance in a distributed setting? And so yeah, most distributed systems like Spark or Dask will have some web page you can go to that will give you, progress bars and will also show you, I spent this much time serializing data, I spent this much time moving data around. We'll see a little bit of that in the distributed section with Dask things, but all the projects have something like that. Yeah. So visual diagnostics are very important to help you understand performance. And you can often shoot yourself in the foot if you don't have some mechanism to figure out why things are costly. Okay, I think I'm going to hand it over to Aron to talk about some data science applications. This, then break. And then, so we'll do one more notebook. I think we'll take a break after that. And then we'll switch into the distributed computing section, and we'll all play with some clusters. Did you want to switch out notebooks or laptops?
So my name is Aron Ahmadia. I come from parallel computing. I see at least one Hawaii sticker here. I was born and raised in Hawaii. My first real job was work at Gemini Telescope, and my very first experience with parallel programming was in 2001, where I wrote MPI and Fortran. I went back on to the Gemini Telescope where we did some parallel programming there for some adaptive objects models and simulations, and that was also done in MPI, but not with Fortran, but with MATLAB, which was a substantial improvement. Eventually, I found my way. We're good?
Your audio is not out, but the screen is on.
Yeah. The screen's up.
Screen's on. Yeah.
Cool.
You can press OK on that.
Eventually, I found my way to the Python world after much tugging and screaming. I actually came in from the supercomputing side of things. So I worked in a supercomputing laboratory in Saudi Arabia, King Abdullah University of Science and Technology. We worked on several Python programs that we ran in parallel. Now I work for Capital One. I lead a data science team in DC. We work on several things, including voice to text and text analytics. I still get to do parallel Python, but not nearly as much as I do other types of things. But everybody on my team gets to do parallel Python, which is fun. Okay, So what we're going to do here is we're going to talk about sort of a more rubber meets the road example of using Python and parallel Python in kind of your daily lives. So who here considers themselves a data scientist or a machine learning engineer? You raise your hands. You'd be proud of it. Okay. So maybe about a quarter of the audience. Who here maybe does something that's data science-like but would never want to be called a data scientist? Fair. Computational scientists? Okay. Did I miss another job category? Software developer? Who here does something that is not one of those three categories? I'm just kind of curious. Okay, what do you do? Engineer. All right, perfect. All right. So like mechanical, aerospace, naval engineer. Okay. Anything else? Yes. OR. Okay. Awesome. Okay. Yes. Yes. Okay. Wow. I must have been like shorter and like younger, and it was about 10 years ago. Yeah. Okay. Awesome. Okay. So we're going to talk a little bit about data science, and what we're going to do is we're going to build a machine learning model, and then we're going to do some naughty parameter tuning. Not so naughty, but I want you to understand what trade-offs we're doing as we do that parameter tuning. So the first thing we're going to do is we're just going to load this up, and since we have scikit-learn installed through our Conda environment, we have some default data sets that we can play with, and we have some default algorithms that we're going to use. So we're going to use a support vector classifier, and we're going to try and solve this problem, which is sort of a classic problem in sort of machine learning, AI, and that is somebody has given us a set of digits that have been scanned by a computer or a device of some sort, and we want to know what those digits actually correspond to as a number. So turn this image, this representation of a number, to, oh, that's the character 0. This is a big problem. Actually was solved by the post office because they needed to route zip codes properly, and so this is all done in an automated way now. But before, you could imagine this was this process. And of course, if you get these wrong, it's a huge deal. You never want to miss a zip code digit. You get misrouted mail, and people get unhappy. So there's this machine learning model that we're going to tune, and we're going to try and make it as accurate as possible. And of course, we're going to use parallel programming in Python to get there. Okay. So we wrote a little bit of code, and it's not in the notebook. It's in a separate module file called cvparams.demo. And so if you want to go in and look at that code later, you're more than welcome to, but I just want to import that for now. And these functions are fairly simple. We're going to do cross-validation, so we're going to split our code between sort of a training set and a validation set. We're going to have some code that, given a proposed model and given some training data, goes ahead and runs that model and then validates it against the second half of the split. And then the final thing we need to do is show our results, so that's the plot results function. And here's where we're going to be adventurous, or we're going to be exploratory. We're going to explore the parameter space of this support vector classifier, right? So scikit-learn, if you say, hey, I want a support vector classifier, it'll happily give you one. If you don't specify any parameters to that support vector classifier, it's going to pick some for you. And how those parameters work for your problem is just going to be slightly random. So you're always better off knowing exactly how to tune these parameters for your model. So we only have 3 parameters here, which is not too bad. 2 of these are sort of more specific to the support vector classifier itself, and then tolerance is just basically a more general one, which is as we iterate through the model at some point, or as we try to sort of tune the model, it's how quickly we decide to stop. So if you want to spend more time tuning the model, you would increase or make your tolerance smaller. And frequently the 2 parameters you care about in terms of how they affect the model are over here. That's C and gamma. Okay. So I'm going to go ahead and continue to execute. Okay. So obviously we're traversing a very high dimensional space. Right now it's 3 dimensions. And we're taking a log space. We're looking at C from values of -10 all the way to 1,000. We're looking at gamma parameter values from -10 to 1,000, and then we're walking over the tolerance as well. And so you'll see that the numbers that we're traversing here are quite large, and so you can imagine that if we pictured this three-dimensional space, we're actually very, very sparsely sampling from it. So if there's any sort of interesting structure in here, we're not going to catch it, we're not going to notice it. We're just kind of going to have some directional feedback on where maybe the right parameters are. So who here can define C and gamma in terms of a support vector classifier? Okay, good, one. So only one person can correct me if I get this wrong. I had to check notes on this. C is basically an error tolerance parameter on the support vector classifier. If you can imagine the space of what we're trying to solve, we have all of these digits, and we want to separate them basically into 10 different classes, the digits 0 through 9. Now, every once in a while, our support vector classifier is going to try and draw lines. If you think of this two-dimensional space where there's a bucket of digits over here, and those are probably the zeros, and a bucket of digits over here, and there's probably ones. But every once in a while, we'll have something that really looks like a 0, but it's actually a 1. Right? So somebody just drew a loopy 1, and it's labeled as a 1. And we need to be able to accept that that thing that really looks like a 0 is actually a 1. And for the support vector classifier to do that, we actually have to give it this sort of soft margin parameter that says it's okay to have some errors. And so you increase that C when you're willing to accept sort of these softer boundaries between things. And if you don't think that those exist, you should actually keep your C very, very small if you think that the parameters or the lines between your classes are very, very tight. So even though we're treating these things as just random numbers, like we're just going to choose one of these, they actually have meanings. And there are trade-offs in your model that actually happen as an effect of choosing these. So that was C. Gamma is another one. Gamma is the choice of the influence of the radial basis functions in the support vector classifier. So the support vector classifier is basically this collection of these sort of radial functions. So if you're thinking, if you come from like the finite element method, or you're like more of a numerical engineering person, think of these as sort of your support. There's this choice of functions, and there's this basis that you're operating over. And if you have a high gamma, you've got these really wide supports, or these Gaussian radial kernels. If you have a small gamma, they're very small. And so the way this translates to the way your model works is your bias variance trade-off. And so a high gamma is going to lead to a larger sort of variance trade-off. So you're trying to almost overfit your model when you increase gamma. So those are the things to pay attention to. Now we're totally ignoring what those parameters actually mean, and we're just going to randomly search over them. Okay, so first we're going to split our data classically into a training and a testing set. And this is sort of scikit-learn's way of labeling things. You'll see this x_train, x_test, y_train, and y_test. So x is your inputs, y is sort of your labels. Okay, so x is the digit picture, y is the label, and then you have a training set and a testing set. Okay, and so this is, we're just going to turn this into, or it's already been turned into vectorized data for us. And now we're going to run this and try it over our entire model. And lo and behold, training models takes time. So as we go over this space and we parallelize over this space, we go and we grab a coffee, we talk to our neighbor about what our favorite new deep learning network setup is, and then we come back hopefully around 10 seconds later, and we have a set of scores for how our model did. Okay, and the sampling here is these little purple dots. The model did okay, and then these yellow dots, the model did quite well. And as I was kind of hoping, the model is doing better in cross-validation when we don't overfit it. Okay, so we have over here a higher tolerance for allowing the model to sort of draw lines, fuzzy lines, so it says, hey, I'm not going to try and capture every nuance of the difference between the classes. And on top of that, I'm not going to draw these super wide kernels that have this big impact and also kind of allow me to overfit. So that said, I want you to go a little bit deeper into the parameter space. And so first, I want you to parallelize our sort of approach here to searching through the parameter space. And then once you do that, I want you to create a more fine-grained parameter search than this one over here. Are there any questions, or are you ready to get started? By the way, you can use any parallel programming technique that you've encountered up until now. You are free to choose. You are not allowed to use MPI. Okay, great.
Is there anybody here who's not hit the big blue button or doesn't know what I'm talking about? Okay. So either check the Slack channel, or I'll do it again here.
We can chat a little bit more about, actually, I'm going to run afterwards, but feel free to.
How do I get a new tab? Or I could just do it here, I suppose. So if you go to PyCon-parallel, it's also in the Slack channel or on the GitHub page. It's PyCon-parallel jovian.org. If you click this giant blue button, click it just once, it should take you, after a few minutes, it should take you to a prompt for a password. The password is PyData, all lowercase. It's written here. If it doesn't happen for you after like a minute, please let me know.
Jupyter Notebook is fine. I could be, but I want to, I want my Emacs, I want my VI, I want my Z shell. You might use it? Okay. So I'm going to do cross-validated, and Matt, then you're going to introduce distributed. In the second version, right? Okay, cool. All these cool kids with their alpha versions of their software. I stick to the enterprise release. Okay.
Does anybody have it not? Does anybody not have it working right now? Everybody moved on to the cluster. What does that mean?
Okay. I want you to, if at any point you have problems with the cluster launching that big blue button, wave your hands and or throw your nearest object at Ben, but nothing heavier than a pound. I don't want to injure him. Okay, he's too valuable. All right. So let's take a look at a couple of the solutions. So this is a thread pool executor solution. So the first thing we do is we just grab, I'm going to just, move this up until it's at the top of my screen. Oh, that's as high as it's going to go. Okay. So we just grab this list of param samples, so we're turning it into something that we're ready to execute through or divide up. We split up the CV splits. So the CV splits are just a list of cross-validated sort of examples to go through. Then for each of these parameters, we're just going to submit that job, and then we append it. So what we're doing here is we're just using this nice submit architecture. We could have done a map here. Instead, we did a submit, and then we collect the results at the end. So I'm going to go ahead and execute that, and I probably should have executed that while I was talking about it, but what I'll do now is, oh, that wasn't too bad, is, oh, I didn't bump up the size of the grid, so you're still not getting a whole lot of interesting solutions. We'll do this again in the distributed with way more. here's another solution, and this is a Spark solution. So for those of you who did this, by the way, using Spark? Okay. Okay. Oh, well, yeah, let's look at how everybody solved it. So who here used map? Okay. Raise your hands high. Like, be proud of what you did, right? These are all valid solutions. Okay, so who used map? All right, yeah, all right. Everybody who did map, good job. All right, everybody who did submit, raise your hands. Awesome, okay, the clear favorite. Okay, so everybody who used Spark and was successful, great, awesome job. Who used Dask? Yeah, okay, cool. So I think a couple of you actually solved it more than once, because I counted more hands and votes than I had people in this room. Maybe people just switched votes, I don't know. Okay. Awesome. So here's the Spark solution that one of you got. We get ourselves a Spark context, which is basically our parallel execution environment. This isn't going to work if we don't have Java and Spark installed on our system, but if it is working, we basically set up these two parallel, what I would call distributed data frames. They're a way to split up data across multiple Spark processes. Then we basically just do a Cartesian product out here, and then we map from there. So we have the, oh yes, the Cartesian product of the parameters with the splits, because if you did not have that, you would be in trouble. Okay, and then you do the map of each of these individual objects, and then what you're splitting out here is the particular choice of CV split and the particular parameter. So hopefully nothing too magical in here. I am going to take us out of this notebook, and we're going to pause on data science for just a moment, and Matt is going to introduce us to how we do this in parallel, not just on your laptop, but potentially on a cluster or a large machine. Oh, possibly we're going to pause and talk even more about big clusters.
Okay, great. So actually, let's start here locally and increase the number of maybe CV splits or parameters from maybe 10 up to 50, because now we have a bit more computational power. We can parallelize. Let's use that. Let's use that to explore our space a little bit. So it's gonna take maybe 5 times longer, but again, we're using all my cores, so I'm using 400 CPU, 400% of my CPU, which is nice and satisfying to see. And it's still taking a bit because it's now doing quite a bit more work. But hey, it finished. We can plot these results, and we get now a much more populated version of that plot. We're starting to see a little more structure here. This region down here is definitely nice. It's green here, so maybe it's not quite as sharp over there. So maybe there's something wrong over here. Not quite sure. So we want to fill in this plot more. We can use parallelism to sort of survey this space a bit better and get better insight. Also, we should give credit where credit is due. This example came from Olivier Grissel, who did a nice talk about it. I think it put out of Berlin a couple years ago. So we're stealing his work. Okay, so, but I would like to do this maybe not 50 times, but 5,000 times. And that would take, we'd be sitting here very awkwardly, honestly, for a while. So let's do the same example, but now on the cluster. So let's look at distributed cross-validation. So on this cluster, there's some notebooks. One is a notebook on distributed services. So you now have a 8-node cluster. Each node has 4 cores, and I think around 6 gigabytes of RAM. 8 gigabytes of RAM, great. That you can use either with Spark or with Dask. You can do things like RDDs with both. Dask will also give you like a concurrent futures implementation. So this tiny notebook, notebook 6, is just showing you that you can connect to both of them. Hopefully, yeah. So you can see sort of the resources that you have available to play with. Additionally, so I'm going to, so I work on Dask. I'm totally biased towards Dask, so I apologize if I say bad things. Additionally, there's a dashboard for Dask, so let's bring that guy up. I know this is actually going to totally fail on JupyterLab. The link is,
'cause it's
relative, yeah. But I can
That's what you get for using alpha software, man.
I support the SciPy ecosystem. I'm willing to experiment. They've actually been, I was playing with JupyterLab last week. They've been extremely responsive on issues, and it's been a pleasure to play with. So I recommend people play with this. Okay, so let's go look at the same notebook again. So notebook 7 is the exact same as notebook 5, except that now, as we're going to run through all these things, so now at the bottom, we're going to okay, so we have again this sequential solution from last time. We're going to parallelize it, and we can parallelize it. I recommend. Okay, so we're going to load up the solution from the last section using concurrent futures, and that'll work fine. Or we can import a different executor, a distributed executor, from das.distributed. And I'm kind of forgetting what the address was put into it, so I'm going to look back at notebook 6, which tells me how to connect to Spark. I can copy these lines. Also tells me how I can connect to Dask and copy these lines.
Slow down for a second.
Yeah, sorry, thank you. So again, notebook 6 will tell you how to connect to either Spark or Dask on your cluster. Dask can give us a concurrent futures interface that we use on a single machine. And Spark can give us the RDD interface that we also use on a single machine.
Can I just check that my DAS connection is working on notebook 6 by looking at client?
Yeah, sure. So I notice here I'm rendering client, and it's showing us that it's connected, showing us how many workers we have. We can use client.submit, just like we used to do before. Maybe we'll make a, oops. Maybe we'll make a function to add 1 to a number. That'll create a future.
So,
So we see-
everybody, please try and get the Dask scheduler up so you can follow along here. You have a Dask client. It's this cell right here below Dask. If you execute that, you should get a client back. Can you all raise your hands if you have that client? All right, looking good. If you don't have the client, the international sign for distress is 2 hands waving like this. Go ahead and give that to us, and we'll try and sort it out. Okay, I'll let you keep going.
I'll endeavor to be slow. Aron reminds me that I sometimes speak quickly. I will endeavor, for a short period, to speak at a more casual pace. So, in Notebook 7, we have this solution from the last notebook using the thread pool executor. We're going to comment out the creation of the thread pool executor, and instead copy and paste how we created the client from the last section. I notice this example is using E for the executor, so I'm just going to call my client E to make everything a little bit easier on myself. So that just ran. Unfortunately, my dashboard is not behaving itself. And we actually zoom in here a little bit and see what just happened. So Dask ran all of our evaluate one functions on that cluster, and it gave us a result back. So we can plot those results. And again, we're using just the same set of small numbers we saw before. Now we have this larger machinery. We can do many more calls. So I'll go up here. I'm going to increase from 10 to maybe 500. I'm going to call that again. That's a great question, Aron. How do I get to this dashboard? There's a link right here, actually, inside of this same notebook.
And that's going to work if I'm using,
The Jupyter notebook.
what if I'm using
then you're out of luck.
Okay.
Yeah.
I just need to fix the URL if I'm in Jupyter Lab, right?
Correct. Yeah. So this gives us the ability now to scale out our concurrent features workload to many more cores, and to get a much better picture of that space we're trying to sample. Again, if you don't know machine learning, that's fine. We're just calling this function a bunch of times and getting values on this two-dimensional space or three-dimensional space. We're visualizing it.
Yeah, who was able to get the dashboard up and submit a job and see the task executing? Okay, who would really like to see that and has not been able to do that on their own computer? Okay, a couple of people. All right, put up the international distress sign. All right.
So exercise for you all. We're going to load up the solution, again, the solution that Aron went through with Spark. And that solution is currently using Spark on our local machine. So here we're saying local 4. That's saying, please start a Spark cluster on my local machine with 4 processes. Instead, you want to point Spark not to your local machine, but to this cluster running. And you can do that by going to this notebook and copying how we created Spark. And then try that same computation again in a cluster. Maybe increase the size even more and see if you can get a better picture when you're plotting your results. So if you have run this cell once with your local machine, sorry, this is a question that came up. I don't want to stop it. Keep bustling. That's fun. But if you're running the Spark problems, you see you can't start more than 1 Spark context per process. So if you start Spark locally here, like I'm going to do right now, and I run this. Actually, that'll take a long time because I'm on the long. Sorry. If you run Spark context once with local, you need to restart your notebook, start a new Spark context with pointing to the cluster. You only have 1 Spark context per cluster in normal settings. So maybe just don't run this cell before you change the address. You need to put something here, and that something comes from notebook 6. So the question is, should sc.stop take care of that? Does it take care of that? Well then, yes. You can also call sc.stop, and that seems a much nicer way.
Okay, quick pulse check. Who has gotten a Dask solution going on their own? Big, wave your hands really nice and high. Okay, who is still going and wants some more time? Okay, who has given up and is staring at their screen and facing an existential crisis of whether parallelism and Python really go together? Okay, they do. Okay. So it sounds like we're ready to move forward in a moment. I just want to take us through a quick recap of what we've talked about so far. I think that's always helpful in a tutorial setting to kind of understand the top level what we're doing. So hopefully everybody came in this morning wanting to learn a little bit more about how they can program in parallel in Python, how they can take advantage of running code concurrently or simultaneously to take advantages of or stop or avoid the problems of network latency or disk latency or these other issues. So some of us have come in with previous experience in frameworks like MPI or multiprocessing, and what we're trying to show you here, what we're endeavoring to show you here is the modern techniques, the best practices that are commonly used in daily Python programming to solve these problems. So one of the first ones that we went after was the map, right? So I have a list or I have a sequence, I have something that has a collection in some way, and I want to apply the same function to every single one of those, right? And we showed you a thread pool executor, and we showed you a process pool executor, and we talked a little bit about the differences between threads and processes. And at the lowest level, right, threads can be friendlier and easier to use. You don't have to worry so much about things like how you serialize your function and how you ship your data around to other processes. They can also be lighter weight and faster. The process pool can be a little bit heavier. It requires a larger effort on behalf of the operating system to keep track of things. And there's a separate memory pool for each of the tasks that you're operating or running. And frequently you have to care a little bit more about how your function or your data serializes. So if you're working with a complicated object, then this might be more interesting. So again, we're reviewing Matt's slides here. Of course, he put me in here with no context, so I have no idea what's coming next. Am I getting ahead of the game? Okay. These are your slides. I don't know them. So let me keep going over where I was going. So we have map, and then we talked a little bit about submit, right? And submit, everybody gravitates towards. As soon as you get the concept that you're passing a function around and you're passing its arguments around, it's a very friendly and flexible API. I want to submit a job. Okay, I'll take care of it, or I'll look at it later. And okay, so who here was paying attention when we talked about what happens when an exception occurs, and they know what that exception looks like? Raise your hands nice and high. Okay. This is the danger of a tutorial, right? We're talking, and then we talk while you're working, and then half of you miss something that was really important. So let me go over it again, because it's really cool. If you submit a job, and that job or that function call raises an exception somewhere, when the result comes back, first of all, you don't see the exception yet. But when you inquire or look at the result, you'll see that it is returned, and that in the return, an exception was raised. And then if you try to process that result, if you try to get what was coming out of it, that's when you'll raise an exception on your side. So you have two ways. You don't even actually have to raise the exception. You can actually just inspect the result and say, hey, did something go wrong in this process? It's actually a little bit trickier sometimes in parallel execution context to know something went wrong. So it's good to think about that error handling and what we'll go from there. So we talked about map, we talked about submit, and then we started talking about collections of objects, and we started going into parallel frameworks where the data is in essence parallel, as opposed to just submitting jobs one at a time or through a very simple interface. So we talked a little bit about Dask, and we talked about Spark. And in a lot of ways, these two are functionally equivalent. I don't really have as big of a stake in the Dask Spark conflict as Matt does, and it's not a conflict, right? It's a choice. So if you're moving into an ecosystem or an enterprise environment or a research environment where Spark is prevalent, you can use everything you're learning here and apply it with PySpark. That's the opportunity you have here, and you can sort of attach in and use PySpark as part of your day-to-day. And the same concepts that we're learning around data frames, around how to set up your jobs and how to execute them will apply. If you're in a Pythonic environment or for some reason you are not interested in using Spark, you have this opportunity with Dask to get your parallel computing, to run in a distributed manner on a cluster, even to run things locally, to build up a task graph for how you do things. You're getting a very gentle introduction to Dask in this tutorial. If you want a more advanced introduction, you can come back next year and take the Dask tutorial, or you can look at the slides that were presented in the videos that are presented over in the other room in parallel to this one. The last bit that we did was sort of a hands-on introduction where we did some data science, and we sort of blasted a number of function executions through. We did it first on your local computer. Now we're doing it in Dask, or Dask and/or Spark, and we're doing it on a cluster. So we press that really big blue button. We're executing the notebooks and on an 8-node cluster. Each of you has an 8-node cluster on Google's compute engine or Google Cloud, which was generously donated by Google and then wrangled by Ben, and has been being wrangled by Ben. He's simultaneously supporting this tutorial and the other tutorial, so we should. Say again.
Great. So, sorry, we're diagnosing a cluster issue in the background. As Aron said, we're doing two tutorials simultaneously. Some of the cluster issues, we apologize. It's been interesting. It's been an interesting couple days. So I'm talking for about 5 minutes on just basic on threads, processes, and data communication, some extra costs to think about. Ben then is going to talk about how the cluster system we've set up works. You don't need to pay attention to that, but it's sort of nice to see how these things work. You as a user don't need to care, but if there are administrators in here who think about running clusters for other groups of people, that will be of high use. Then Ben will talk a little bit about some costs and give an example of some costs of communication and algorithms. If during all that talking you don't want to listen to us talk, you want to do some things, I recommend going to Distributed Data Frames, Notebook 9, wherein you can play with some CSV data using sort of a parallel pandas implementation. And that'll be sort of a fun thing to play with. I recommend having the dashboard up too. But we'll get to that notebook eventually, maybe briefly. So if you want to do something in the background, that's maybe a fun thing to play with. So people ask me outside, talk about threads, talk about processes, why do I care about one versus the other? Aron has shared some thoughts about that. My general suggestion, if you're using anything that is based on C or Fortran, or anything like NumPy or Pandas or scikit-learn, any of the numeric Python projects, you should use threads. You'll be having the data in the same process. There's no cost of communicating data between different processes. A process is like a different program. When I say process, that means program. When multiprocessing, you got many different Python programs running at the same time. They've got to like send messages back and forth to each other, and that overhead can be really costly, as we saw earlier today. We had computations that took 2 seconds or then took like 20 seconds because of that communication. Now, when we switch to distributed systems, we have that same problem again. But now, rather than communicating data between different programs on the same computer, we're communicating data between different programs on different computers. We have to go on the network. We have to go maybe on the internet. So it becomes much more costly. And so we become very, very aware of moving data around. So we were taught computer science, taught programming. We were taught about the cost of for loops, the cost of memory access. Well, there's this new cost now that enters into our equation when we think about computational costs. There's other things that we lack now. We maybe don't have like a shared hard drive that all of our tasks see. We maybe don't have the same software environment everywhere. Things become more complex. We have solutions, like what Ben will talk about in a moment, to solve some of those, but there are new sort of problems that have been thrown into the mix. Systems like IPython Parallel, or Dask, or Spark, or TensorFlow, or many systems follow a centralized distributed system model. There's one program in the middle, the scheduler, which is coordinating many workers. Those workers are actually running our Python functions for us. And there's us, a user, the client process, who's submitting jobs to the scheduler to then run on the cluster. So this is generally speaking how Spark or Dask work. And Ben has set up all of these programs for you. When you click that button, it's making all these programs and running them on different machines. But yeah, there's some new costs to think about. So if you think about things like communication, so moving data between different machines. If we're using threads, we have sort of infinite bandwidth. We can move data for free. If we're maybe doing inter-process communication on the same machine, move data maybe like 300 megabytes per second, something like that. I mean, it can be faster if you use fancy things, but if you do things naively, it'll be about this speed. If you're on a network, you might get down to maybe 100 megabytes per second, maybe worse, depends. So these costs increase as you go to larger and larger systems. There are also problems about moving functions around. So functions may be small, but it's not clear how to turn them into data sometimes. This is often a problem when you want to run maybe a custom computation or a custom object and have that occur on a different machine. And so any parallel programming system needs to turn your function into a string of bytes, then move those bytes across a wire, and then reconstitute it. It's a bit like in Star Trek, the teleporter. So you have like a crew member stands up, I want to go beam me down to Earth. It has to be like turned into little bytes that then get like transmitted somehow down, and then reconstituted up. And that process can be, as you've seen in Star Trek, that process can be flawed sometimes. So the thing that comes up that is a challenge sometimes. Moving things between computers is like teleporting them, and could be some challenges. Ideally, systems like Spark or Dask or Python Parallel have tried to hide those things from you. And if you're doing common things, you'll be fine. But those do sometimes come up. There's also uniform environments. We generally expect that like your version of NumPy or Pandas is the same on all of your computers. And that can be challenging sometimes. So if we were to make a cluster out of all of our laptops using our normal Python environments, we would have like 20 different versions of Pandas running. And that would cause a challenge for us as we're communicating things. So I'm going to, with that, hand off to Ben. Who wants this page.
I think that's right. Yeah. So actually, I would slightly disagree with what Matt said, that users should care about this insofar as that they should know what to go back to their labs and say, this is what we demand. You should be able to satisfy these reasonable requests. So I heard some people were doing MPI jobs, maybe use schedulers like Slurm or Torque or things like that. Do people in here use other kind of big data schedulers like Yarn or Mesos? Does that some people do. Okay, so for the people that have, as Matt was kind of mentioning at the end, for people that are using these batch schedulers, you probably have like this thing called an NFS mount. Does that sound right? So your home directory or the scratch space is kind of replicated wherever your machine or wherever your job runs. And Python has this problem of being able to ship binaries around. So Java doesn't have this issue. You can compile everything into this big jar that gets distributed everywhere. So for people that don't have this NFS mount, you have to generally come up with something a little bit more creative. There's lots of solutions for that. So when we think about moving to a distributed setup, and we want to handle lots of people, we have to generally think about these kind of four larger issues of how are we deploying all of our different applications, whether we need to support multi-tenancy for lots of people, whether there's a queuing system for resource management or making sure that any one particular job doesn't hog all the resources of the cluster. And then, as I was saying just before, how do we replicate this kind of inherent problem with Python? How do we replicate the environment for wherever that job might run? Right? It might run on bare metal. In the case of batch jobs, it might run inside of these Docker containers. Actually, how many people here are familiar with Docker or have heard that? Okay. How many people know about Kubernetes or Docker Swarm? Okay. So some, all right. So as I was saying before, the way that we can kind of think a little bit about environments is we can kind of preload the environment there. In the case of the NFS mount, the environment kind of moves around with us. We can try to ship that environment in a way that can be met by some kind of spec. So we can hand it like a pip requirements file or a conda lock file or something and say, wherever that job runs, go pull down those packages for that particular node. We can also use this other thing called Docker that seems like most of you are familiar with, where we've preloaded all of the packages inside of an image, and we say, just run this particular image. And it seems like a lot of people are kind of moving in the direction of either shipping the spec or doing a lot of kind of Docker magic under the hood. That's not to say that these systems don't exist, and it probably will continue to exist for long periods of time. I think NFS and Slurm have been around since like the 70s or 80s, right? We're still using them. They're still incredibly vital. We need to still support those kinds of things. But for a lot of newer tech stacks where people seem to be moving in the direction of Docker. So the way that this tutorial was built was generously donated with funds from Google. And we use this tool called Kubernetes, which largely acts as this giant all-knowing scheduler for resources and for Docker containers. So you can go to Kubernetes and say, I'd like a container with 8 gigs of memory and 2 cores. Go provision that for me and go run this particular image over there. And that's what happens every time you click that button. So our architecture for this generally looks like this. There's this big blue button. That is actually just a Tornado app that's been replicated a couple times. You hit this proxy app that's running for something that, if people are here familiar with Jupyter ecosystems, it's the configurable HTTP proxy. And when things successfully load, your notebook goes through the proxy and hits one of this head node in this. Does the mouse work? Yeah, this head node in this kind of list of containers here. So there's one special container that's a scheduler, and then we've replicated 8 workers for you. So it's actually 9 containers per machine, and that's kind of amazing that actually not just everybody in this room, but as Matt and Aron have said many times before, like 100 other people in the other room down the hall are all have access to a 9-node cluster with 8 gigs per node, and generally 2 cores per node as well. And we did that all with the click of a button. So when you go back to your corporations or institutions, wherever that may be, you should be able to expect kind of this level of support from people that say, I want a cluster, I want to do exploratory data, build me a giant blue button is a reasonable request in 2017, right? That is not a joke. You should be able to really say to your DevOps teams or whomever, or you yourself can just build a giant blue button that does, deploy my setup. Okay, I think that's enough philosophy for now. Yeah. So I need to get out of here. What? Okay. And all right, so we're going to look a little bit at kind of communication patterns and some algorithms and making kind of judicious choices. So oftentimes we are presented with some data, we're doing a little bit of exploratory work, or not, we just need to return the top end results. And we're going to look at that in two different ways. Here we're going to use Spark to show a limitation that Spark has, but also a limitation that Spark has in terms of how it's built internally. But all these things could also, all these same ideas and deficiencies also map to Dask as well. Well, not all of them, just the larger ideas, the algorithms here. So we're going to generate, you've already done that, we're going to generate, what is that, 10 million? 10 million random numbers. Let's see. We already got an error. Oh, okay. If people are having problems loading this Spark context, I would suggest just killing the kernels in the other notebook where you first loaded Spark. Spark has a little bit of issues when you run in multiple notebooks. So we're going to build this data frame of 10 million random numbers. What? It should be, yeah. All right, onwards. Okay. So we have this data frame, and we're going to actually we're going to sort of bounce a little bit back and forth between the data frame and the underpinning store of the data frame, the RDD that you've been playing with before. We're going to call two algorithms that are going to answer the question that we had before of what are the top five, or what are the top five values of the sorted list. And we'll see that one of these will go much faster. Does anybody have an idea of which one will go faster? How many think that sort by will go faster? How many people think top will go faster? Okay, why do you think top will go faster? Less code. There's less. Oh, there's less. There are less characters there. That's a good reason. Yeah. You've already tried it. Okay. It's still taking longer than. Does anybody have another answer?
Top five will only be about first top five. Doesn't need to start everything. Just get the top five.
Exactly. Yeah. Yeah. That's the right level of approach here. Yeah. It's just trying to find the top five. It doesn't have to sort the whole thing. So when we call sort by is really going to sort our entire giant list of elements. It's going to go through each one, and then from that, it's going to pick out the top five. Right. This take five is going to pick out the top five of those. Whereas top five is going to do this much more intelligent kind of sorting of of the data and can pick out the top five. Actually, what's happening underneath is as you see, it has 100 partitions. So what it does for each partition, in this case, it will say, for each partition, sort the list, tell me the top five. And then once it has all that, it will then move all that information up, and it will take all of those lists, sort them, and then call the top five. And it keeps on doing that until you get the top five. So it does that a lot faster. This is still, okay. How do I get a new tab? Or Control T. Okay. Great. Okay. So we see that it takes 13 seconds for sort by and 314 milliseconds for top. So our choices for how we solve problems when we move to these distributed systems actually will greatly impact our our interaction with the cluster itself. Like if I'm doing exploratory work, I want things to be snappy. If it's less than 10 seconds, I'm generally happy. If it's more than 10 seconds, I'm generally getting really distracted and I'm going to go check the news. So, and it's just going to impact everything. But we can also still stay within within the data frame. We don't have to drop down to these RDDs. So a lot of complaints that you'll hear about Spark is actually that it's generally slow if you go to this PySpark API if you're just working with the RDDs, and that's the argument generally given is because you're often moving data back and forth between Python and Scala. So we have to convert a Python int to a Scala int or a Java int. We have to convert dictionaries and convert all those data structures. So the less time we spend converting, the better off we are. In this case, what Spark has kind of pushed as a really good solution for this problem is actually this concept of this distributed data frame. So when we built this with this random DF, we dropped down into the RDD. We can just sort and take the top 5 here. We should expect this to actually be kind of on the order of or close to the top K. But notice that we have the data looks a little bit different. We have this row uniform equal. It's sort of still it only converted kind of at the end of our call. So we're going to see the same sort of problem space and solution with a very common operation with group bys. So here we're going to grab public GitHub data. This is every event that happened in January 1st of 2015. So by event on GitHub, it's every time a pull request has been submitted, every time a PR has been, a PR has been committed, requested, an issue's been filed, an edit. Anything that you see on GitHub gets logged publicly, or anything that happens on the public GitHub pages gets logged. So we want to, generally a good question might be like how many events of each kind have taken place, how many issues, how many comments, and we're going to go after grouping all of those events. So we're going to do a little bit of specific Spark work. We're going to take all that data and we're going to load it into memory. So the df.cache, and then now we're operating on this dfc object, is just we took this GitHub archive data that was JSON, and we loaded it all into memory. So our workers don't have to do a lot of fetching from S3 or even pulling from disk. It's all there for the taking. And again, just like we saw before, we're going to drop down into the RDD layer. So I have this JS thing, and we have around 200,000 events, and we're just going to look at one of them. So here's the URL. Somewhere in here is an event. Franklin Gu was the actor, but you can sort of see where we're going with this. And we're going to call the most naive thing that we can, we're going to call the group by thing. So Spark came from the lineage of MapReduce. Are people here familiar with MapReduce? So it has this lineage of I want to map something, I want to group by something, and was for a long time was just significantly faster than MapReduce. So I was saying before, the data frames kind of have pushed things along significantly. But here, if you approach these problems naively, you can end up in fairly long and painful time periods where you're just sitting around waiting, twiddling your thumbs. So here we're grouping by the type, and then we are we're mapping each type to itself and how many there are, and we're collecting all of them. So you can see that there were almost 10,000 issue events. There's 177 public events. You can kind of go through and play with this data, but what we're focused on here is how much time it took, which is 15 seconds. You can do the same sort of thing with a more complicated thing called a combine by key, which will go a little bit faster. And combine by key is doing what these two things these two plots here are displaying, which is the same sort of problem that we had before with top K. We want to group something instead of doing a giant shuffle everywhere and putting everything into its own bucket, causing a lot of communication overhead. We're just going to group locally and send the message back. So a nice metaphor for what's happening here that we've used several times, and I apologize for the gendered example, is if you wanted to group all of the boys and all the girls and count how many there were inside of an entire school, you could tell everybody to go into the halls and sort to one end of the school and the other end of the school. but that would just take an enormous amount of time because all the kids would get lost, or not get lost, but they would, I don't know, just get into random fights or go into the bathroom or, I don't know, do not what they're supposed to do as you can possibly remember from being a child or even as an adult when you're told to do something in a large group. But things just take a lot of time. Instead, what you could have done is said, every teacher count up, assign this as a project for the class to do, count up how many boys and how many girls you have and report that number back to the principal. And the principal could then decide. And that's what's happening here. That's generally the kinds of things that we're after when people look for optimizations in distributed computing is how much work can I do locally before I have to pass that message on? And again, we can do that same thing without having to drop down into the RDD world. We can still do this inside of this very comfortable data frame API that all of us are generally used to at this point in time from pandas or from R. And we'll see when Matt presents in a second, Dask also has this data frame interface. So we've gone from, I think it was like 13 seconds or 15 seconds to 3 seconds to 1 second, all for the same question, or the same answer to, or they answered the same question. Are there any questions here, or should we keep going? Everybody's comfortable with this? Great, okay.
Okay, yeah, so just to recap, we've seen that, as Aron said, our cost profile of computation has changed significantly as we're in this space where memory is no longer always available to us. And the things we might do, like sorting a list and then taking the top 5 elements, might be very slow to do in that context, and we've built new operations like top K. Ben gave a good example of group by, which is an operation we commonly do in Python, maybe in pandas data frames, but that can actually be quite slow if you actually need to move all of the kids to one side of the field, all the kids to the other side of the field. That's very expensive when you're not in a classroom, but you're in a school with many classrooms. The nice thing about data frames is that because they're a bit more high level, projects like Spark can reason about your intent and say, oh, no, we don't actually want to group by them. We'd like to do something else. I can rewrite your intent to something that I know to be more efficient. So we use these higher level abstractions, things like data frames, that can make things feel more fast, more pleasant. Okay, so I'm generally assuming people are somewhat comfortable with pandas. If not, please let us know and raise questions. So the next notebook, we're going to look at Dask data frames, which are a pandas-like API that is the same sort of thing. So what we're going to do is we're going to play with data that's on the cloud. So we have a bunch of CSV data sitting on Google Cloud Storage. And we can read a little bit of that data with pandas. So I'm opening up one of those remote files, and I'm reading just 5 rows of data. This is the New York City taxi cab data set. It's a common data set used in presentations. It's sort of an inconveniently large data set that's still pretty understandable. And this has every cab ride in the city of New York for the year 2015. So it has, when the cab picked up the rider, how many riders there were, when they were dropped off, the locations, breakdown of the fare, etc. On disk, this data is about 20 gigs. In memory, it's about 60 gigs. We don't have that much space on our laptops, but we can use our cluster to start dealing with that data. So the first few cells in this notebook, this is notebook 9, are just going to set up your client and then start reading that data. I like using the dashboard while I work, just so I can see what's happening. So I'm not going to use now the pandas data frame read CSV function, because that won't work. That'll try to create a pandas data frame that's very, very large. So I'm going to use the Dask data frame read CSV function. That's going to break up my computation into lots of little data frames spread around the cluster. And so you can see that Dask is reading all these blocks, these different machines, and producing lots of pandas data frames for us. And so this df object is like a pandas data frame. It has the same sort of API, but when you operate on it, it's actually operating all these little pandas data frames spread around the cluster. So if you are familiar with pandas, you can sort of jump right into things and start playing with computations, doing basic pandas operations, filtering, aggregations, group bys, etc. If you're not familiar with pandas, it's a good time to learn. Pandas is a great API for doing general tabular computation. So there are a few sort of examples of kinds of computations you can do. The one difference that'll show up is that you're going to, at the end of a computation, so here we're selecting, all of the positive fares, so df.fairAmount where fair is greater than 0. We're selecting down a few columns, and we're making a new data frame, which is just these columns. When we call persist, we're saying, please make this computation concrete in the cluster. Otherwise, everything will be lazy. Yeah.
New on the existing data frame or a new one because your bytes stored didn't change from you?
It is a different one, but let's. In this case, it did whatever pandas would do. So it may have. Let's ask me later.
Okay.
Yeah. So we can start doing some of these operations that we're familiar with doing pandas. Can I get a show of hands who is like rockstar pandas user? Who is like backup singer pandas user? Okay, who has never used pandas before? Okay, there's a fair amount of us. Great. Okay, you should wave your hands wildly, but if you also don't get this, that's also fine. So in the Pandas API, I can do things like filtering. This is kind of like NumPy, if you're familiar with NumPy. But I also pick out certain columns, and I can look at the data that results. So here we're seeing a few of the columns of our data set, just the first few rows, where the fare was positive. The syntax is hopefully somewhat familiar or somewhat intuitive. I can get the tip amount column. I can figure out where the tip was 0. So every time where the cab rider was stiffed, or didn't receive a tip, and I can find out how many of them there were. And there were, in this particular data set, which is 12 million long, looks like there's, or 120 million long, looks like there was about 5 million that were at 0 fare. So we can answer some questions on a large data set. And this is just the Pandas tutorial at this point. You're just experiencing the same API you're used to, but now with larger data sets. Okay, so for exercises, there are a few things you're asked to compute, like the average of the passenger count column, how many cab rides are in a cab on average. And so you're going to do basic Pandas operations, like these operations. Get the passenger count column, call the sum method. And then when you're done, so you've constructed this computation, you call compute, and it's going to ship the computation out to the cluster, execute it for you, and give you back a result. So let's spend a little bit on that. If you're not familiar with pandas, that's okay. This is not critical, but maybe play with it and see if you can get some of the syntax.
Hey folks, how's everybody doing on the exercise? Who has completed the exercise and is ready to move on? Okay, a little bit less than a third of you. Who is almost there? They've just got it figured out and they want a little bit more time? Okay. Who has yielded? Okay. Nobody has submitted, so I suppose that we should just talk about this a little bit. How's that sound? Okay. So I'm going to try and solve this live, which I bet there's a solution below. Oh, there is no solution below. Okay. I'm going to try and solve this live. I'm probably going to get it wrong. So if I mess up and I get stuck, I'm just going to rely on somebody to have posted the solution into Slack. And I'll head over there and use their solution instead of my own. So for those of you who have never seen Pandas before or a Pandas data frame, what we're looking at really under the hood is actually just it's a NumPy array. It's a set of records, and there are always some number of columns and there's some number of rows. So think of it as a two-dimensional table. And so some natural analogs, an Excel spreadsheet, potentially a SQL table, a set of records from either a specialized database that's maybe a NoSQL record store, or maybe just a flat file like a CSV file. So all of those things represent pretty naturally as a Pandas data frame. And one thing that you get with the pandas data frame is these nice labels for each of the column headers. So in this case over here, I've got df columns, and what I'm interested in looking at here is, let's see, I've got 3 options here. The mean of the passenger count column, the mean trip distance grouped by passenger count, and then the final thing that I can do is create a new data frame that filters out all the rides greater than 3 miles. So one of these I know how to do for sure, and that's the passenger count column. So if I just, there's 2 ways to access it. This is slightly more correct, but also doesn't give me that nice tab completion. So I'll just go ahead and do this. And then I can just ask for the mean. And then remember that if I do just this, I'm not going to get what I want. I have to do one more step, which is to call .compute. Okay, was everybody comfortable with here? They got this far? So even if they'd never seen a pandas data frame before, it looked kind of enough like a NumPy array that they could just, treat it like one, grab the column. The nice thing is having that name that they can just refer to and then calling compute. This would have also been totally kosher. Right, I can explicitly reference that series, then I can grab the mean, and I can compute that. Okay. I promise I'll only show you 2 different ways to do things. I won't do it 50 different ways. Okay. So the mean trip distance grouped by passenger count. Okay, I'm going to roll up my virtual sleeves here and try and do this in a slightly more complicated way. But what we want now is trip distance. Okay. And we want to group this by passenger count. So and I get an error. Passenger count is not a legit key. Okay. Now what did I do wrong here? Okay. I gotta do the group by first. Okay, so if I just group by passenger count, what do I need to grab out of this to get what I want? Yeah. Okay. So now I can do the group by. I don't need to do a compute here, right? I can just grab trip distance. Okay. And then I can, oops. Yeah, I'm missing a mean. This is going to go terribly for me. All right, so we have a number of trips that don't involve any passengers. I don't know how that works, but that's impressive. We also have the party cabs down here with as many as 9 riders. This is New York City. It's a very strange town. I've never been in a cab with 9 people in it before, but apparently the average distance is about 7 miles when it happens. And you can guess that these are probably the standard folks doing larger rides. It is interesting that as the number goes up of passengers, the ride distance goes down, right? So it's maybe a group heading to a bar or something like that. Yes? The 14 and the 18 or the 2 point? Okay. That would make a whole lot of sense. So people are all trying to leave New York? Is that what I'm trying to get out of this data set? Or coming? Fair. Okay. There was another question? Yes. Yes. You couldn't get it to tab complete columns. I was just doing that, right? Maybe I wasn't. Let's check. Make sure, of course, that you execute to create the thing that you want to tab complete on in that cell. I assume you're doing that, but if you're not, so like if I was just, in this example, I have this. So first of all, if I do that, I'm not going to get it. right? Because you don't get tab completion on attribute lookups. But if I do this, and I do, that's not a good example. This is the good example. If I did this and I did this dot here, yeah, IPython doesn't know it. Was it giving you that? Okay. Okay. Have faith and believe. It can be done. Okay. Now there's a hard one. Create a new data frame that filters out all of the rides greater than 3 miles, then compute the above quantities again. So I'm going to go up in my my notebook, and I've got passenger count mean, and I've got, oh, I did this twice. I'm just going to delete this cell. Okay, and I have group by. These are the two things I've got working, and I want to figure out how to do this with a second data frame where I have filtered out, and I'm going to do it my way, and then Matt's going to tell me how I should have done it. What is the name of this field? Oh, is it trip distance? Okay, so the ride better be less than 3 miles. So that's kind of how I would do it. Is that a good idea? Bad idea? Uh-oh. Okay. 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 Ah, that's right. So I didn't need to create it. I just needed to create a reference to this thing that I wanted. But let's go through here and check. So we did a persist where we filtered. Okay. And as expected, the mean trip distance is now not greater than 3 because we filtered everything for those greater trips. Okay, so those are the first set of exercises. I think that there are more. There's an example here of trying to debug problems in parallel, which is I'm not. Matt and I both had that shrug. If you're having problems with parallel code, I can recommend a few strategies. The first and the most important one is make sure you have a serial version of your code that is perfect. It's tested, it's logged, it's debugged, it does everything as correctly as possible. Do not try to write new code in parallel. It will always end poorly. Okay, so I know some people, that's a truism. They're laughing and they're nodding their heads because they've dealt through the pain of this on whatever system they came to before they came to parallel Python. So what's true in other languages and other environments is also true in Python. We're not giving you a magic elixir that makes parallel programming substantially easier. We've gotten some patterns that will be simpler and that will work better. As soon as you start doing something, outside of, hey, taking sums and means and filters, you're going to be doing something more sophisticated and you might have some problems. So like I said, try and focus on small problems, get everything working with small data, and combine the complexity of your code in manageable ways. And definitely write tests, write logs. These will all help you sort of unwind problems as you sort of encounter them, and as you put together bigger and more complex systems. Should we move over to tuning, or okay, perfect.
Thank you, Aron, for taking over that. So again, this is not a DAS tutorial. It's convenient for us because we know a bit more about it. Generally speaking, data frames should be, if you're comfortable with them on a single machine, the objective of many of these parallel libraries is to give you that same experience in distributed setting. Sometimes it works well, sometimes it's challenging. Someone asked about, hey, where's the median function? There is no median function because median is actually really hard to do in parallel. And so it's interesting sort of where they break down and where they fail. So for the last notebook, we'll look at performance tuning. And that's not the notebook that I want. And I'm going to try, so you may have noticed this dashboard to the right, which shows us many things. Okay, so the last notebook, we also need to change a couple of things because we're on a slightly smaller cluster than we were last time. So we're going to read the same data set again. In this notebook, originally, we're looking at all of the CSV files. You will run out of RAM on your cluster if you do that. So instead, just look at one. So this is the same. Also, you need to import GCSFS to make this work. This is just if you import the Google stuff, then we can start reading data from Google a bit better. So there's 2 changes you'll need to make in order to be happy with the rest of this exercise. So while that's running, absolutely. Yeah, so in the file name, originally it was an asterisk here. That's saying read all of the files, give me data for the entire year. That's around 60 gigs in RAM. Our clusters only have around 48 gigs. We'll make a couple copies, and that's going to sort of blow things out a little bit. You'll get a bad experience. So instead, we're just going to go with 1 month of data. It's around 2 gigs on disk, around 6 gigs in RAM. That'll be pretty comfortable. Okay. So you may have noticed this dashboard over here to the right. And this is showing us what our cluster's been computing on over time. I'm just giving you a moment, Aaron. But thank you for the question. Yeah. So this is showing us over time on the x-axis what all of our workers are doing. So we have 32 worker threads and what they're doing that time. So here we're getting an item. We are calling the less than function. This is one of the examples that Aaron was doing earlier. These are bokeh plots, so I can play with navigation here. If I also want to get a full screen version of this, which I think I do, go over to this tasks screen. So now as I run a computation, like here I'm going to repartition my data set a little bit. That is hopefully going to update these plots. This is where we've been having problems. Have people actually been experiencing these things updating live? Usually they update live. You are seeing experience that you're having problems, or you're good? Okay. So we've been having. My notebook is now forbidden. What that means. Okay, sorry. I'm going to start a new cluster. Ben, if I start a new cluster, is that okay?
Yeah, I would believe the other
Okay, so in this exercise, what we're going to do, we're going to play with some parameters. So we have some choices in these distributed data frame situations or distributed arrays. For example, we might have data that's split among 100 different pieces. So we've got 100 different pandas data frames around, and our DAS data frame is coordinating all of them. Or we might have only 5 pandas data frames around, and we're coordinating all of those. And there's some costs and benefits to either one. When we do various algorithms, we also have some choices. For example, Ben was talking about calling top k to find the top biggest arguments, top biggest elements in a collection. We might find the top 5 in everything, and then take maybe a group of 10 and find the top 5 of those 10, and then do this again in sort of a pyramidal structure. Oh, in that case, let's open up some old tabs. And so this notebook, what we're going to do is we're going to play with those parameters, and we're going to get different performance. There we go. Okay. So we're seeing on my screen live as these tasks finished. And the bars are colored. That corresponds to the kind of task they're doing. So here we're seeing it's reading some block of bytes from Google storage, and it's calling the pandas read CSV function on those block of bytes. So it's broken up by one CSV file into lots of different pieces, and it's reading those pieces. And so what we're going to do for a few minutes, I'm going to run some computations. I'm going to look at what happens on the right side of the screen. I'm going to use that to gain intuition about cost and distributed setting. Then, for the exercise, you guys are going to play with some parameters, and then also look at that screen and see if you can get that computation to be as short as possible, as fast as possible, by playing with those parameters. So that's the last exercise we're going to do. And someone over here had a question earlier of like, are there visual diagnostic ways of understanding how performance looks like? And this is us playing with that. So I have my data frame, and I'm going to break it up. It's currently in 32 pieces. So I've got, I think, 32 cores, and all those cores have about one piece. But I might want many, many more pieces. In fact, maybe I want 1,000 different pieces. So now, rather than 32 pandas data frames around my cluster, I have 1,000 pandas data frames around my cluster. There's all much, much smaller pandas data frames. And we saw that happen here, right? We saw it calling these sort of millisecond-long tasks, and it called many, many of them. So now this data frame 2 object has 1,000 partitions. And so I'm going to compute the passenger count sum computation on both data frame 1 and data frame 2. Which one will be faster? So let's just guess. People will likely be wrong. It's fine. So data frame 1 is composed of 32 pandas data frames. Data frame 2 is composed of 1,000 pandas data frames, but they're much, much smaller. Data frame 1 will probably be faster per data frame because it's bigger blocks of bytes. The CPU can be a little bit more efficient, but there's going to be more overhead on the 1,000 block one. So let's run them both and let's see which one is faster. Here's with 32. So you see it ran a bunch of sum functions. Red in these plots is communication. So it communicated all that data to one machine, and it called sum again. And in total, that took around 69 milliseconds. And with data frame 2, this is the 1,000 partition data frame. I should have called time on that. Took a bit longer, took about a second. It did all of these small computations, did a bunch of tiny communications, then it's finished. This algorithm is tunable with a parameter, split every, which you guys are going to play with. And so rather than take all of these 1,000 pandas data frames and move them all to one machine, we can take maybe every 10, and we'll add those up. So we'll do that maybe 100 times. We'll take all of those 10, we'll take all of those 10 and add them up 100 times. And so this might look a little bit different. There's lots of much smaller communication, lots of much smaller red blocks in here. And it runs a little bit faster. So as an exercise, play with these parameters. Play with the repartition parameter up here, this 1,000, and play with split every. And let's see who can make this computation run the fastest. And you may be able to get some insight about what's taking time by looking at these plots to the right. So let's do that for a bit, and then we'll see if people can provide some numbers for the best number of partitions and the best number for split every. Okay, let's do that for about 5 minutes. So sort of midway through, does anyone have any experience they want to share? Any particularly good or particularly bad numbers for the number of partitions and the split every parameter? Someone's saying 4 partitions. And split every probably doesn't matter in this case. Yeah, around 30 milliseconds. So what actually took time in that case? We spent around 3 to 4 milliseconds per partition computing the sum. So NumPy, or pandas, can sum over these now. So these pandas partitions are now sizable. They're like 500 megabytes each. The series column, the passenger column is smaller, maybe many tens of megabytes, 100 megabytes. But we can sum over that column in a very small amount of time, in a few milliseconds. And so in previous examples, most of our cost was in overhead, because the computations were so fast. But two partitions doesn't give you faster? So we actually see here that, so this is showing the memory use on those machines. There's 2 machines right now that have, looks like 4 gigabytes used. We're getting close to the point where they're going to run out of RAM. These are sort of small machines. They're telling you that you should sort of be aware. Let's try with 2. And that is a little bit longer. Any other feedback?
People delete on DF2 to remove it. I think it's duplicating it every time you call persist with a number of positions.
Yes, the question is, should we be deleting DF2? And you can, so we deleted it. You see the memory went down, but Dask is going to handle garbage collection. If you rewrite over it, it'll figure it out.
Okay.
Your
Duplicate 3 times over itself as you change the number of positions. So I didn't know how long it would take to do garbage collect that.
it would happen quickly. So the Dask memory space mirrors your Python memory space. For as long as you have some pointer to some remote thing, it will keep that data in memory. Once that local Python object goes away, Dask will see it go away, and it will release the data on the cluster as well. You don't need, for instance, you don't need to worry about it. Dask will do the same thing that pandas would have done, or Python would have done generally. Yeah. Yes, the question is, so Dask, you see in the docs before that Dask will spill to disk. Same with Spark or many other systems will spill to disk, which means that when they run out of working memory, they'll start dumping some of that memory onto the hard drive rather than crashing. So Dask will start taking, it has a bunch of all these different pandas data frames in its memory. It'll find the least recently used ones and it'll start to write them to the hard drive. This is generally fairly slow, so you get a pretty high performance degradation when that happens. But yeah, that would work fine. If you give Dask like a giant pandas data frame, it just can't fit that in memory, and it will crash. So you can still make things crash, but you have to try a bit harder. Okay, so as another example, let's now look at not Dask data frame, but Dask array. I'm going to restart my cluster just to clear out old things. And so here, rather than having like a tabular data set, we're going to look at an n-dimensional array. This is a 2-dimensional array. It's 1,000 by 1,000 array of numbers that's composed of a 10 by 10 grid of NumPy arrays. Each NumPy array is of size 1,000 by 1,000. And so we can see we constructed that random array by calling the NumPy random function 1,000 times or 100 times. And you can do computations like matrix multiplies and such. And these computations will depend very heavily on this chunk size. So we might consider changing this chunk size from being 1,000 by 1,000 to maybe we'll have really wide and short rows, maybe 10 by 10,000, or maybe the other way around. We might have many small blocks or many large blocks. That will also affect our computation. So here we're seeing, doing this matrix multiply, we're seeing lots of computations. These are the NumPy tensor dot operation overlapped with lots of communication. So again, so the question is, so this chunks argument is maybe misleading. It refers to chunk size or chunk shape. It is the shape of one individual chunk. Yeah, this warning is saying, hey, the operation you're doing the operation you're doing requires a lot of tasks. This matrix multiply is a complex thing. You might want to consider reshaping things or rechunking things to avoid this blow up. It's just it's a guidance thing, but it'll still work fine. So that computation took a while. It had a fairly large memory footprint. If you watched this space, it increased in size to about 7 or 8 gigabytes. And we can change some of those parameters. But just like in the situation, we can do things like y.sum along some axis. And it'll do some computation for us. So we're out of time, but the rest of this notebook is again playing with some of these parameters and looking at these diagnostic dashboards to try to think about how to tweak the algorithms that you've been given. Things like Spark or Dask array or Dask data frame or Dask bag will give you these sort of nice canned systems to play with, but even then they have parameters. And those parameters are affected by the bandwidth of your network and how big your data set is, and et cetera. So there's things still to play with and to learn about. Hopefully you can find visual diagnostics like what are here to help guide that understanding. So here in this computation, we're seeing mostly dead space. It's mostly white. Most of the time, none of the workers are doing anything at all. So Dask is actually being very inefficient here. So you might ask questions about why that is. How can we make this computation just much more full of color and hopefully much narrower? So, okay. Ben, Aaron, any other things you want to say?
This is definitely the most impressive class I've attended. You guys moved really quickly, so give yourselves a hand. I know everybody who comes into these tutorials comes with a vast range of experience.
I know everybody who comes to these tutorials comes in with a vast range of experience. So some folks had never seen a data frame before. Some people have been doing parallel programming for 10 years. I hope all of you got something out of this. I hope you learned something. I hope you saw something you hadn't seen before, got to play with a technology that you hadn't played with. Please, the feedback is super important for us. We want to make sure that this is a better tutorial every time we give it, so that this is the worst version of the tutorial we've ever given, right? And then we can give a better version next year. So let us know what we could have done differently, how the presenters discussed or topics we covered, specific material that we gave too much attention to or not enough, something you came in expecting to see and that you didn't, and vice versa, right? What was surprising, what was delightful? Of course, we always like to hear about things that you really enjoyed as well. That's also as important as the critical feedback. Ben, do you have anything?
So talking about parallel stuff is really fun. It's also really painful. As you can see, I want to just throw in just a little bit of advocacy for before you go down the parallel track, sometimes the better option is just getting a bigger box. And that option is totally available to you for those people that are lucky enough to have access to cloud computing resources. Amazon and Google and Azure have boxes that have a terabyte of memory. Put your data into just a single pandas data frame and do operations there. That sometimes is, the only way to win is to not play at all, or something like that.
That's a good closing comment, I think, for parallel computing tutorial.
I'll go ahead and put on a nuance on that. You'll actually find that if you're dealing with maybe a 20 to 30 gigabyte data set, having a small Dask cluster, if it's doing what you want, like 8 to 16 nodes, will be much faster than trying to do this with a single node. And that actually happens to be because you have, say again?
For 20 gigabytes, I use a single node. For
Yes.
a terabyte, I'd use a 6 to 8 node cluster.
Sure. The trade-off actually starts happening in that 20 to several hundred gigabytes range. And it has to do with the speed at which you can access data. A lot of it is actually how well the data is stored on disk or in whatever place you're chunking it from. You can gain something frequently by going to a parallel cluster. But you can see here the three of us have different experiences at which point we'll turn over and switch to a cluster. We'll all, at 10 or 20 gigabytes, probably start with a single node. And then somewhere in that 100 gigabytes to a terabyte switch over. That's a guidepost. Your own experience is going to be different with the particular data that you have.
How long does this cluster stay on?
How much you got?
So probably after everybody leaves, I'm going to blow away everybody's clusters. You can start over, and I'll keep things around for maybe the rest of the day. But
in a much smaller
a much smaller size. So if you get like if it doesn't load for you after a minute, just message me in the Slack channel, and I can reset things and get you going again if you want to keep playing. That's a good question.
Great. Thank you all.
Thanks all.